Okay, so this was fitting of the temperature if you really can expect the temperature, so you are basically assuming Boltzmann distribution. But there's also another feature in this program that does not assume anything like that, and it's hidden under this button called Boltzmann plot. So if you press that, it opens a new pop-up window which looks like this, and here is the same measurement as you can see here. So of course the measurement shown here is affected by the number that you select here, that's just purely copied into this pop-up window, but only one of the measurements. And then we would like to perform another kind of fit. So here are offered all the simulation databases that we have at the moment paired with the measurement. So at the moment it's only one OH-AX transition. So I will just want to use that for fit. I can restrict the fit to some maximal vibrational and some maximal rotational number, but if I don't want to do that, I just leave the negative number here, and in that case it will just use anything in the database. Lines at least means that it will ignore all the upper states that don't have at least two lines in this spectral window, which is the safe assumption. If you want to be even more safe, you can increase the number, but basically it shouldn't be greater than 6 for OH, because there are no OH states that have more than 6 lines in this spectral window. So I've just checked this box, and I can press this hidden fit button. So I will just do that, and here you see that something changed in the console. And we have to wait a bit, and now the fit is done. So this is the fit without the assumption of Boltzmann distribution. And what you see here is the Boltzmann plot, basically. This divided into the upper vibrational states 0, 1 and 2. So if I uncheck the 2 and 1, they just disappear from the plot, and here you see the Boltzmann plot of the vibrational state 0 in the upper electronic state, and it looks pretty straight actually. If you have some different measurement, for example a discharge in contact with liquid phase, with water or something like that, it probably wouldn't be straight like that. But in the case of microwave atmospheric pressure discharge, it's pretty safe to assume that there is a single rotational temperature. And if you want to compare the temperature with the one in this window, so it was something around 3000 Kelvin, we can try to select some range of the states like that. We don't have to restrict it because it's really a pretty much straight line. So how do I do that? I just press the right mouse button and make a lasso like that. And if it's selected, we can just calculate rotational temperature, and here you see the straight line that was the best fit, and the calculated temperature is slightly less than 3000 Kelvin with this estimated error. Also here you can see that it's changed quite a bit. That's because here I have selected only the states that are from the vibrational 0. So here you can see what corresponds, what the spectrum would look like if only the selected states were responsible for the emission. So for example, if I clear the selection and select only one of the states, I can just do show selection, and you see that if you select one state you will see 1, 2, 3 lines, maybe 4. Basically it's actually 6, because here are always the very very small one which are less probable. So you can do that for any state you wish, and you see that now it's more because I have selected 4 states. This basically allows you to judge if one of the points is completely off, like here. You see that this doesn't make a very straight line, so I can just clear selection and select these points and see how much can I trust them if I compare them to the measurement. So I will just show selection, and I see that these are these very very small lines. So basically my decision is don't trust that too much, because it's really trying to compare these small things on these big lines. So this helps you to select the points that really make sense. And you see that basically on average the slope may be slightly less than it was for the 0 state, which would correspond to slightly higher rotational temperature than is shown here. And indeed you see that the rotational temperature is slightly higher, but basically the difference is not great, and comparing these two numbers can give you a better estimate of the error. Here you see that it's plus minus 40 Kelvin, but as we have already seen, this is probably underestimated. So if you report these errors in your articles, be careful and try to think about a better way than just copying this number. Okay, so that's the Boltzmann plot, and if I am now satisfied with what it looks like, I just select all, and I can save selection as CSV again. So what I can do now, okay, it's not the Boltzmann, it's not an expert of temperatures now, it's Boltzmann plot. Okay, I should correct my mistakes and save the file, and now it's here in a neat CSV format.